Hello everyone, and thank you for attending today's webinar, Getting the Most Out of an Amptek X-ray Spectrometer, Intrinsic Noise, Dead Time, and Interference. Before we begin, I'd like to cover a few housekeeping items. At the bottom of your audience console are several application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget and submit your question. We'll try to answer these at the end of the webcast, but if a fuller answer is needed or we run out of time, you will receive an answer via email. A copy of today's slide deck and some links to additional materials are available in the resource list widget, which looks like a green folder. You can expand your slide area by clicking on the maximize icon in the top right or by dragging the bottom right corner of the slide area. If you have any technical difficulty, please click on the help widget. It has a question mark icon and covers common technical issues. An on-demand version of the webcast will be available approximately one day after the webcast and can be accessed using the same audience link that was sent to you earlier. Now I would like to introduce today's presenter for today's webinar, Robert Reedus. Robert is the Chief Scientist at Amptek, an Amptek company in Bedford, Massachusetts. He has spent over 30 years designing instruments for radiation detection and measurement for many applications and for many customers. He has spent most of the past 15 years concentrating on X-ray spectroscopy, primarily for X-ray fluorescence and energy dispersive spectroscopy. He has developed state-of-the-art silicon drift detectors and SiPin detectors, high-performance digital signal processors, and worked with customers using these components in a wide range of applications. Prior to that, he developed instruments for gamma ray spectroscopy using compound semiconductors, scintillators, and HPGE detectors for homeland security and for medical applications. He also spent over 10 years developing instruments for space radiation measurements. He is an author or co-author on over 40 technical publications, is a senior member of the IEEE, and for several years he has taught in a short course on radiation detection and measurement at the IEEE's annual Nuclear Science Symposium. Now over to Bob.
Good morning. Again, my name is Bob Reedus. I'm the Chief Scientist of Amptek, and I'll be speaking today on getting the most out of your Amptek X-ray spectrometer. This is the second in a series of webinars talking about how to properly use the Amptek spectrometer. The first webinar, which we presented a few weeks back, talked about measurement, precision, and accuracy and how that related to some detector parameters. Today I'm going to be talking about intrinsic noise and dead time and interference or system noise, giving background information on these and some advice on how to address them. The third webinar will dig into the details of how to actually set up parameters and such within our spectrometer. Why are we talking about intrinsic noise and dead time and interference? There's really two reasons. The first is that there are fundamental theoretical limits to the performance of any X-ray spectrometer. These are really driven by the noise and by dead time in some peaks. When customers want to optimize a system, misunderstandings about these limits really drive about half of the issues, half of the questions we have. So that's a really key reason to spend a little time understanding them. The other thing is, Helmut Spieler, a scientist from Berkeley, once famously said, after assembling a radiation detector system, a common experience is that it doesn't work as expected. Half of the questions and problems that customers have arise due to system and system integration issues, and they make it appear that the noise theory doesn't matter. So that's why we want to talk about it as well. So this webinar will give the background behind the most common problems, misunderstandings, and limits. I'm going to talk first a little bit about pulse shaping, what it is. The last webinar made it clear I needed to talk a little about that. Then we'll talk about intrinsic noise, what is it, what's expected, how to minimize it. We'll talk about random timing, which drives dead time and pileup. And then we'll talk about electromagnetic interference or instrument noise and some strategies to minimize that. So by talking about pulse shaping, several people asked the question, what is pulse shaping? What is the peaking time? Things related to pulse shaping. So just to step back a little bit, in any radiation detection system, there's a few main components. You have the detector. The radiation deposits energy in the detector, and that gets converted to an electrical signal. And what comes out of the detector, the output from the detector, is a current pulse. The preamp integrates the current. There's a little picture that sort of shows a cartoon of what the signal looks like. So you get these steps that come out of the preamp, and so that voltage steps or the preamp output, it's difficult to measure that directly. They're small and superimposed on noise. So that's followed by a circuit that shapes the pulse. And by shaping, we mean we tailor the time and the frequency response. You want a short response in time to minimize pileup, but you also want to filter the white noise to improve the energy resolution. So that's what the pulse shaping is. It's tailoring the time and frequency response to optimize the measurement. The output of that gets digitized for subsequent analysis. There are types of shaping that can be used. The plot on the upper right shows some analog shaping circuits that were used for many years. These are based on conventional high-pass, low-pass filters. You can get all sorts of different pulse shapes, Gaussian, pseudo-Gaussian. The bottom plot shows the digital pulse shapes, where we have a trapezoidal shape. And in modern X-ray spectrometers, digital processing is almost universally used because it has better performance, lower noise, and minimum pileup. So by pulse shaping, what we really mean, or by giving a pulse shape, we mean that when there's a current pulse out of the detector, we get a trapezoid coming out in our digital processor. Within that trapezoid, the time it takes the trapezoid to rise from 0 to its peak is the definition of the peaking time, and then there's a flat top across the top. That's the definition of the flat top time. And it's important because the peaking time really dominates both the noise and the maximum rate you can handle. The peak height, that's the dashed curve, that pulse height correlates with energy, and by measuring the pulse height, we know how much energy was deposited. The energy spectrum is formally a pulse height spectrum. It's important to note that that pulse height is relative to a baseline. The baseline isn't necessarily 0. And there's what's called a conversion gain, which is the ratio between the amplitude in either volts or in channels to the energy deposited in EV. It's also worth noting that you can have in a digital processor multiple channels, multiple signal processing paths, so that we have the blue trace shows an output for our slow, what's called the slow channel, which is optimized to filter the noise best. The red shows the output for our fast channel. It's also a trapezoidal shape, but with a much shorter time, and that's optimized to separate pulses in time. So you can have multiple, and we do have multiple signal processing paths optimized for different purposes. These are just oscilloscope traces that show actual measured pulses. The top right, there's a preamp output. You can see the preamp steps, and you can see the shaped trapezoids that we get out. The bottom left shows first one X-ray that's independent, and then two that have a little bit of overlap in time. They're close together so that the shaped pulses overlap, but the peaks are separated. The middle one, they occur so close in time that you have just one pulse. And then the one on the bottom right is zooming in on that baseline, and you can see fluctuations in that baseline. That's the noise that we'll be talking about in a couple of slides. Our attention to intrinsic noise. First question, what is noise? And the strict definition is that it's any unwanted disturbance that's superposed on a signal that obscures the signal's information content. In radiation spectroscopy, we have these pulses that we've seen before. The noise modulates the baseline. So the signal pulses are riding on this fluctuating baseline, and the fluctuations in the baseline are the noise. There's two types of noise: intrinsic noise, that's generated within the circuit itself, within the components in the circuit, and extrinsic noise, also known as interference, where it's generated outside a circuit and energy couples in. So what are the consequences of noise? This sketch here on the left shows it's a simulation of pulses riding on top of noise, and on the right there's the pulse height spectrum actually measured. And there's a few consequences of the noise. First, it gives a minimum threshold. If you cannot distinguish signal sitting in the same range as the noise. So you have to have a minimum threshold that eliminates your ability to measure the low amplitude signals. If your threshold gets set too low, then you get false counts, which is an erroneous measurement. That shows up in the spectrum on the right as that little spike of peaks at the lowest channels. That's because the threshold is set into the noise. And the other thing is that the fluctuations, the pulse height sits on top of that, so you get fluctuations or uncertainty in the pulse height measurement, and that causes the full width half maximum. That affects the resolution of the peaks. The variation in the pulse height, the pulses on the left, lead to the peak width on the right. The detector response function, the noise is important, but not the only factor in the energy resolution. The full width half maximum arises from both the noise and what's called Fano broadening, and that's inherent to the physics of how radiation interacts in a detector. At low energies, the noise dominates. As you go up higher and higher energy, the Fano noise dominates. It's important to note there are many other factors that determine the full response function of the detector to radiation. There's escape peaks, there's scattering, Compton scattering, Auger scattering, photoelectron escape. So there's a whole pile of issues. We're focused here today simply on the intrinsic noise. What is intrinsic noise? It's sometimes hard to understand, and I think that a nice example is shot noise, which is a leading source of noise in the detector. In the trace here, the plot shows simulated responses. The red pulses at the top show the current pulses that would come from a detector. They give the red steps out of the preamp, which lead to the red triangles that we see, that we saw from the scope traces. In addition to the current pulses, we have, because we have shot noise, we have a dark current through the detector. There's electrons that pass through the detector, and every electron that passes through creates a current pulse out of the same shape as the signal. It's just smaller amplitude, one electron instead of a few thousand electrons. That gives little steps out of the preamp, and you can see a trace there, little steps that occur at random times. And that causes the baseline to vary. You can see at the bottom the simulated response of the varying baseline due to these little electrons going through. This is now additional simulations where you have a higher dark current. You can see you get more of these steps going along, leading to more fluctuations in the baseline. So the randomly occurring, because electric charge is quantized, the randomly occurring electrons that go through create fluctuations in the baseline, and that affects the noise that we see at our output. That shot noise, which is one of the fundamental noise sources, there are thermal noise, generation recombination noise, there are other noise sources, but they're all similarly arising from random fluctuations in the current through the detector or through the circuit elements within our preamp or shaping amplifier. You can never eliminate this shot noise. You can reduce it by cooling the detector, by reducing the dark current. You can optimize the electronics to filter it out, but you can never eliminate shot noise or intrinsic noise in general from a detector circuit. Several properties. The amplitude varies randomly with time. The probability distribution of the amplitudes is Gaussian, and the noise sources add in quadrature. That's the square root of the sum of the squares if they're uncorrelated. Another key thing is that it's the noise at the input stage before all the gain that dominates. This plot shows, so there will always be intrinsic noise. What's important is to understand what's expected. And there's a few key things. It always is going to vary with peaking time. It's going to be a minimum at some peaking time called the noise corner, and then it's going to increase at shorter peaking times and at longer peaking times. The plot on the upper right shows what's expected for Amptek's 25 square millimeter fast SDD, and you can see the curve of how this noise varies with peaking time. It also always increases at the longest peaking time, and out here it increases significantly with temperature. At short peaking times it increases a little bit with temperature, but not as much. And to operate at high count rates, you want to operate in the short peaking time limit. The resolution then comes from both this noise and the Fano broadening, as the plot on the bottom shows. Each one of Amptek's detectors has a different family of curves. These are listed in our spec sheet shown on the website. You can look them up. But what you'll find is that the fast SDD, it always has the lowest noise and the lowest noise corner, which means it runs at the shortest peaking times, supports the highest count rates, why it's fastest. The SDD will always have second best performance, a bit higher noise, a bit lower peaking times. The silicon pins, you can see at the longest peaking times, so the lowest rates, they're comparable to the SDD and fast SDD. But you run at the shorter peaking times for higher rates, that's where you see the performance difference. This is a plot that shows what's expected for Amptek detectors. This compares the resolution on the vertical axis with the maximum input count rate. And you can see again at the lowest rates the resolution is pretty similar, but if you want to go up at higher rates, that's where the SDD is better than the pin and the fast is even better. Well, given that, how do I minimize intrinsic noise in a detector? If I'm a user, how do I minimize the noise? The first thing you have to do is decide what resolution and count rate you really need for your application. The webinar that we gave a few weeks back talked about the importance of that. So you need to decide how good a resolution do I need, how high a count rate do I need to operate. Given that, you need to pick the right detector. Again, the fast SDD will always give you the lowest noise and the highest count rates, but the others cost less, and in many cases their performance is quite adequate for your application. So you have to decide what's the right detector for your application. Given that, you need to find, again, the optimum peaking time. Do you use the relatively long peaking time, the noise corner where resolution is best, or do you use a shorter peaking time to get the higher count rates? Using what we talked in the last presentation and the charts in the last couple of slides, you make that decision. Then you have to pick the right temperature. I'll be discussing that in the next couple of slides. And then you need to use good signal processing electronics. As I mentioned before, a digital processor with trapezoidal pulse shaping is close to ideal and always gives you the best performance. You can use analog shaping, but there will be performance loss from that. In a good design, with a good signal processing electronics, the detector and the input JFET really dominate the noise. Having said that, I've seen plenty of poor designs where other things can really dominate the noise instead of that theoretical ideal. We recommend using a digital pulse processor. The performance is always best. It does draw a bit more power, but in most applications in X-ray spectroscopy, the performance makes it worth it. Amptek provides digital processors. People sometimes use others. I will say that Amptek's processors are really designed to work with Amptek's detectors. We've invested a lot of design time in really optimizing these processors, and they really provide the best performance with our detectors under the range of application conditions. Turning to temperature, there's two factors that kind of trade against each other in temperature. First, the plots before show that as you bring the temperature down, the intrinsic noise gets better. But having said that, if you looked at those plots, there was really very little advantage to cooling the detector below around 230 Kelvin. If you have the cooling running always at its maximum, you have a problem that affects accuracy or stability. And the problem is that the centroid and the resolution of the spectrum will be changing with detector temperature. So if you always run at full cooling and the ambient temperature, your lab temperature warms or cools, or you take your detector in the field, then you're going to find the centroid and the full width half maximum changing and degrading accuracy. The plot on the top here shows a detector that's run at full cooling as the ambient temperature is raised between 0 and 50 degrees C, and there's a pretty visible shift in the spectrum as the temperature changes. What you can do is to regulate the detector temperature, raise the detector temperature up to a set point that can be maintained, and then, although you have a little bit more noise, you can stabilize the system for better accuracy. So we recommend always doing this. Find the temperature that you can regulate and use that as the set point to improve the system stability and thus the accuracy. Again, these plots just kind of compare. The one on the left shows the noise versus temperature, and it really makes the point below about 230, there's very little advantage to further cooling. You really get a lot of advantage from the stability. The other thing you get if you don't cool as much is reduced power dissipation. The plot on the right shows the power in the vertical axis versus the cooling that you have. And if you don't need to run to full cooling, you will reduce power dissipation, and this can be quite important in the handheld instruments. So our suggestion is to find the warmest environment where your system will operate, set the unit at full cooling, and measure how cold your detector reaches, and then use a set point that's a few degrees above that so you have some margin. How important is thermal design? It's quite important is the answer. This is a plot. The photo shows a little setup. The detector was mounted in a heat sink, but that heat sink is just sitting in air as opposed to the bottom thing shown in the image where the detector is mounted to a really good heat sink. If I have a really good heat sink, my detector can reach 210 Kelvin, but if I remove that heat sink, put the detector preamp just sitting in the air, if I have a fan going over it, it reaches 240. If I put it in a box where there's no air, it can really warm up significantly. And that really fights against both getting good noise and getting good stability. So you really want to look at the whole thermal design of your instrument. You want basically a good thermal path to ambient air. There's only a water, so of temperature of heat to be dissipated, but if there's not a good path, that watt can cause 20 or 30 or more degrees temperature raise. So in a handheld analyzer, you really want to mount the detector case, that is the metal of the package, to some piece of metal that goes to the outside of your instrument. I've seen handhelds where they mount this metal to a piece of plastic, or they're mounted to metal and then encase that metal inside plastic inside the detector, and they lose 10 or 15 degrees right there. So don't cover it with plastic, don't thermally isolate the detector, and use a separate heat sink for the X-ray tube and the DPP. The X-ray tube will be dissipating a lot of power. You want to separate that from the detector. And at benchtop, the big challenge is that the air temperature inside the box warms up. So you need a good heat sink, but you also need some way to get air flowing through the box so you can keep it cool. And the thermal design of the system is really important to optimizing performance. Another set of issues outside of intrinsic noise is pulse, pileup, and dead time. All this occurs because of random timing. X-rays are produced at random times, but they're uncorrelated in time. I will say, I had some questions about pulsed applications. When you have a pulsed system, then the X-ray production is not random in time, so none of the formulas here apply. All of the standard formulas assume you have random timing, so pulsed systems are a completely different thing that I will not be addressing in detail here. Some peaks and dead time occur because these X-rays are produced at random times and because it takes time to process each pulse. And that time is related to the peaking time, and that's related to the noise filtering. So random timing has two consequences. First, there's dead time. You're going to have a time where if a pulse occurs, two pulses occur separated by too short a period, you simply don't detect the second one. You also get pileup, that the pulse heights there's a pulse height error. Sometimes you can separate these pulses, and sometimes there's what's called a sum peak. If the pulses occur close enough in time, it's simply one current pulse coming out of the detector, and there is simply no way to differentiate two simultaneous X-rays from a single X-ray of the same total energy. So time is the time after each event during which the system cannot record another event. Some pulses are going to get lost. There's a true input rate that counts per second coming in, and then an output rate that you measure. We want to know the input rate, and you want to minimize and correct for the dead time losses. Amptek's DPPs do not measure the dead time and use that to correct the output rate. We separately measure the input rate using our fast channel, and we've found that really provides a much more accurate method. Dead time, the plot below shows the output rate versus input rate for a couple of different peaking times. It's important to note that the dead time depends on the signal processor and the peaking time. It does not explicitly depend on the detector. So any detector running at 4 microseconds peaking time will have the same dead time characteristics. But what one typically does is choose different peaking times for the PIN, the regular SDD, and the fast SDD. And that's what drives the dead time characteristics of the different detectors. For our slow channel, there's a maximum output rate which corresponds to a 68% dead time, or a factor of 3 dead time correction. You never want to run above 68% because you're throwing good counts away. We recommend running at 50% or less. As you get above that, you're doing a bigger and bigger correction, and it's easy for errors to creep in. Pileup occurs when pulses are too close together in time and the pulse height of the second gets affected. The result is an error in the measured pulse height, so a distortion in the spectrum. Plot on the upper right shows some sketches, cartoons of pulses showing how they pile up. The bottom on the spectrum shows a spectrum taken at a fairly high rate with pileup rejection turned off. You can see the primary peaks. Then you can see a continuum from pulses that are separated by different times. As they get closer and closer together, the summed peak gets higher and higher, and at the end you get these little spikes that are the sum peaks, and these are two that just completely overlap and give you twice or the sum of the energy of the two input pulses. In Amptek's processors, we have something called pileup rejection, so we have this parallel fast channel which is optimized to detect pulses quickly, and using that we can reject pulses that are overlapping in time unless they're truly simultaneous. If they're within what's called the pulse pair resolving time, we cannot reject them as separate, and so those remain in the spectrum. Plot on the bottom right shows the spectrum taken with pileup reject off, and then with it on, you can see we've removed the continuum due to the distinguishable overlapping peaks, but there are still going to be some peaks from the ones that occur within the pulse pair resolving time. The formula here gives the rate of counts in the sum peak. You can see it depends on the pulse pair resolving time, which is really the fast channel rate. So it's the fast channel peaking time that matters there. So the slow channel peaking time determines the dead time. The fast channel peaking time determines the rate of events in the sum peak. Some sketches that show, these are simulations showing pulses that occur well separated in time in the upper left, and then as they occur closer and closer in time, in the middle you get pulses, there's a little overlap, but the pulse heights are not affected. Upper right, they're closer in time, more overlap. Pulse heights are still both accurately measured, and these are both going in the full spectrum. The bottom left shows two that overlap. There is pileup, and so this is a distorted peak, but the fast channel will let me separate them. The middle, they're closer in time, still separated. The bottom right, they're overlapping in the fast channel, and so these are going to contribute to the sum peak. So processors have a dead time. The plot here shows the dead time versus input rate for various peaking times, and again, it depends on the slow channel peaking time, not on the detector per se. For the dead time correction, we use the measured fast channel to determine the input rate, and these are the key parameters that talk about this. In the next webinar, I will really discuss how to optimize these settings to get the best performance. Finally, I want to talk about the interference noise. Interference is from energy coupling into the circuit from outside. So here's an example of a situation, a problem that I was actually solved not too long ago. I have a detector and preamp, and I also have a fairly high power X-ray tube, and they share a ground. And what happens is that the X-ray tube is taking in current for its power supply, and then connecting it, it's going back. There's a return current that flows through the ground, and the ground flows from the tube to the preamplifier to the signal processor. And the issue is that there's some impedance in this ground connection. And so what happens is the current pulses out of the X-ray tube lead to a voltage difference between the preamp and the processor, and that causes noise. So the bottom right shows what I measure on my oscilloscope. My trapezoidal pulses are sitting on this baseline that looks almost sinusoidal, and it's in phase with the power supply ripple, which is shown in the green. This fluctuating baseline noise leads to fluctuating pulse heights, and that causes the spectrum you see on the right, which are supposed to be nominally Gaussian peaks, are actually split because the noise fluctuation, the intrinsic noise ripple, is bigger than the interfering noise ripple is bigger than the intrinsic noise, so leads to false counts and to peak splitting. So properties of interference is that the output voltage is periodic. It's not random. Like intrinsic noise, it affects the pulse height and the count rate above threshold, but it's limited to certain frequency bands, and the pulse height distribution is not Gaussian. You can by eye differentiate the Gaussian peaks from the non-Gaussian. In principle, you can eliminate it totally. In practice, it's hard to get it completely gone, but it can be made negligible. Understanding interference. To deal with interference, you have to understand you need three things. You need a source of energy that can couple in, you need a coupling mechanism, and then you need a susceptible component. So to solve an interference problem, you have to address one of the three. Either eliminate the source of energy, or reduce the coupling. This may be magnetic or acoustic. It may be a matter of changing the frequency, or change the susceptibility of whatever it is in your circuit. So to solving interference problems, the first thing to do is to find the source of the interference. Basically, interference is going to go away when you turn off the interference source. So your best thing to do is to turn off everything possible. If you can turn off the tube, use an isotopic source, turn everything off, see if you can get to a nice clean measurement. Maybe take the spectrometer out of your system, put it on the midge, make sure it's clean, and then start turning things on one at a time. And when the offending party is, you will suddenly see the noise. You can also use an oscilloscope, because the ripple that you see at the output is going to be in phase with the source. So using an oscilloscope is key. And once you've found the source, then you have to decide which of the three paths is easiest. To turn off the source of radiation, to reduce the coupling, or to change somehow the susceptibility of the circuit. Well, classes of interference, because it's important to understand how the energy can get in. You can get conducted currents. Most of the interference problems have to do with conducted ground currents. That's probably 3/4 of the interference problems. You can get ripple on power lines. You can get radiated with capacitive or magnetic coupling. You can also get acoustic radiation, vibration, because radiation detectors are somewhat sensitive to mechanical vibrations. The key thing is grounding. Never trust your ground. Pay close attention to ground. Always have a real ground connection. That is, make sure your system is connected to local earth ground. Separate the power return from the signal reference. A single point ground is usually best. And consider where the ground currents flow and the ground impedances in your system. Not just resistance, impedance. At high frequencies, it's often the inductance of the grounds that's key. This shows that for grounding and shielding, sort of some typical design rules. There's no one-size-fits-all scheme for minimizing interference, but there are some typical good practices. For example, here we have the preamp. It's shielded, where it's tied to the detector case and to the preamp signal ground. You typically want the case of the preamp tied to the signal ground. That goes back to the signal processor. The signal processor has a single point ground to my whole system and to earth ground. The preamp cable is short as possible, and shielded with that single ground to the DPP. I have the sources of interference, my X-ray tube. I have a shield that I've placed between the tube's high voltage power supply and the rest of my system. You want to shield that as far as possible. And then I've paid attention to the power and communication lines, to the returns, and I'm using low ripple power supplies. Electronics are an issue, particularly with our silicon pins. The STDs and fast STDs are nearly immune to microphonics or acoustic vibrations, but silicon pins, and even more so cadmium telluride detectors, are microphonic. Vibrations in the system will add noise, particularly in the 10 to 100 kilohertz range. Basically, these arise from mechanical resonances in the detector system, so there will be a response from one detector module to the next. So minimizing vibrations is very, very important. So what I've covered today is a quick summary of the background information on pulse shaping, on intrinsic noise and how it varies with peaking time and temperature, the importance of temperature. I've talked about random timing and how it affects pileup and some peaks. And I've talked about interference and system noise that often gets in the way of making good measurements. These are some resources, some additional information that talk about this. They're excellent textbooks to refer to. But I hope this background information will help you better understand how to optimize your system. Our next webinar will get into actually how to set parameters within our hardware and software. Thank you very much for your time and attention.
Hi, thank you very much for attending the webinar today. Hopefully it was educational. We now have time for questions and answers. I see there are a couple of questions that folks have sent in. I'll answer those. If you have more, please send them onto the chat, and I'll respond to them as I can. One of the questions that was asked is about why the pulse height centroid shifts with the detector temperature. That's a good question, and there's really three things that affect that. Most inherently, it's pretty well known that it takes about 3.6 eV to produce one electron hole pair in silicon. So that's the energy per pair. What's not as well known is that value is actually a pretty strong function of temperature. As the detector temperature increases, there are more lattice vibrations, more phonons, and you end up with more energy required to produce one electron hole pair. That's about 150 or 200 parts per million per degree C. So the pair production, the energy required to produce electron hole pair, is a significant function of temperature. In addition, there's a feedback capacitor, and those capacitances always have some temperature coefficient, and those really dominate. You also will get some temperature drifts in amplifiers and such. Those are pretty small, but the variation of gain or signal with detector temperature is pretty significant, which is why stabilizing the detector temperature is fairly critical for stabilizing your system. Let's see. There was also a question about temperature and trying to reach the lowest energy limit. Say you want to get down to 120 eV. If you're trying to measure X-rays at 120 eV, that can certainly be done. The first key is to pick the right detector. The fast STDs have much lower noise, down around 30 or 40 EV, full width half maximum. So pick the fast STD. Use a relatively long peaking time, around 4 microseconds we recommend. And low temperature is important, so getting down around the 230 Kelvin or so, getting below that is not particularly important. But if you were trying to measure that, it would not be possible at the relatively high temperatures. Let me see. Okay, I've got a question about the difference between the fast and the slow channels. So these are basically, think of them as two parallel paths of signal processing electronics, two parallel shaping amplifiers, basically different bandpass filters. And the slow channel is one that has a relatively long peaking time. What that does is to filter the noise most effectively, and so that's optimized to measure the pulse height as accurately as possible. But the problem is it will be affected by pulses that pile up or overlap in time. So in parallel, we have a second signal processing channel that runs at much higher frequency. It has higher noise, but it can separate the pulses that overlap in time. So we have these two parallel channels. One optimizes the pulse height measurement. The other one optimizes the detection of pulses that are closely spaced in time, and we use the pileup as identified in the fast channel to clean up the spectrum as measured in the slow channel. So there was a question about sending out the slides or direct to where you can find them. If you go to Amptek's website, amptek.com, the tab Resources, the tab Webinars, if you go there today, you can see the previous webinar we gave. We gave one a few weeks back talking about precision and accuracy. That's on our website right now. The one we gave today will be posted there shortly. Will be available online, I think, in a day or two. So let's see. Is it possible the total count is higher than the input count? So the total count is measured in the slow channel. The input count uses the fast channel. The reason you might see some differences is because each has an independently set threshold. So if I set my total count threshold down low, say into the noise, and my fast channel threshold high, so that it's missing things, then that would report an input rate higher than the total rate. So you can see that if If you have set the thresholds in the system correctly, you will not see that, but by incorrectly setting some of the parameters, you can see that. The next webinar that will be given 6 or 8 weeks from now, I will discuss in more detail how to set these parameters, how to set the actual, what's the optimum fast channel time, slow channel time, how to set the thresholds. It's a good question. You will not see it if it's set correctly. The question was, given the fast STD is pretty immune to noise, is it reasonable to use an ultralight heat sink and fan directly atop the X123 cooler? So the fast STD is relatively immune to acoustic noise, microphonic vibrations. It is still affected by electromagnetic interference and by intrinsic noise. You can try an ultralight heat sink and put the fan on top of it. Again, there's no one-size-fits-all solution to either thermal design or interference design. There's just a number of good principles. A fan will not only produce microphonics, it has the potential to produce EMI, so you simply have to experiment with what works best in your application. What's the input and output count rate presenting recorded data? I'm not quite sure what that means. I'll discuss that one separately. There's an input rate, and that can be up to 10 million counts per second, and then there's an output rate that follows from that. All of that goes into the spectrum, and that's acquired over time and read out by the spectrum. Link to the slides again. So if you go to Amptek's website, that is www.amptek.com, there's a tab labeled Resources, and under that is a tab labeled Webinars. You will find, today you can find the previous webinar. The one I'm presenting today will be available sometime from now. Yes. Okay, reset lockout time. I didn't discuss that directly here, but what we use is what's called a reset style preamp. What that means is that we show the preamp signals back on, early on a slide. Let me see if I can go to that. You can see the blue traces come out of it. Those are the signals out of the preamp. Each time there's a current pulse into the detector, you get a stair step. And that stair step goes up to a power rail, and then there's a reset signal that restores that. When that large reset signal occurs, all of the electronics, there's a distortion because of saturation. And so we have a reset lockout period, which means we don't record data for the time it takes for everything to restore to normal. So that's what the reset lockout time is. It's the time when we stop data acquisition to let everything return to normal after there has been a reset. It's commandable to different values. Generally, it needs to be longer for the silicon pins and shorter for the SDD and shorter yet for the fast SDD. Again, the next seminar I'll discuss a little more briefly exactly how to set that. If you set it to 0, then you lose no time, but you get a distorted spectrum out. So there's some trade-off between setting that to its longest and shortest. Let's see. Okay, cooler properties to talk about a delta T of 85. Yes, 85 degrees is the maximum temperature. If you're running full current through the Peltier cooler, 85 degrees is the difference in temperature between the detector chip itself and the backside of the detector. Now the backside of the detector may be warmer than ambient. So in fact, in general, it's going to be warmer than ambient. So you can't get 85 degrees cooler than ambient. It's 85 degrees relative to the back of that detector. If you are not running it at full cooling, so if there's reduced current through the detector, through the Peltier cooler, then it does not cool as much. That temperature difference drops from 85 to 75, 60, 50, depending upon how you set that. 240 Kelvin that I referred to is the measured temperature of the detector itself. So we have inside the package, immediately adjacent to the detector, we have a small temperature sensor, and we use that to monitor the temperature that the detector reaches. At full cooling, that's 85 degrees cooler than ambient, which means in a typical lab condition, it should reach lower than about 220 Kelvin. But if you take your unit out of the lab and put it in the field, we've got systems that are used in factories out in where temperatures could be 40 degrees C, and the ambient's 40. It may be hotter inside your instrument box, 45, 50 degrees C, and at that point, the detector does not reach as low a temperature. That's why, for stability, we recommend raising the set point. Within our signal processors, you can command it to go to a particular temperature. If you set it to 200 Kelvin, it won't actually reach that. That simply means the cooling circuit is always driving as hard as it can. If you back that off some to say 230 or 240, the resolution loss is negligible and you improve stability, as gone through in several of the slides. Says, are all detectors still usable up to 68% dead time? So 68% dead time, again, that's the curve for any particular peaking time where your dead time is 68%, that's where you'll get the maximum output rate. If you increase the input rate higher, so your dead time goes above 68%, your throwing counts away. And that's true. That's a function that's simply a function of the dead time properties of a digital processor. So all detectors have a maximum output rate where the dead time is 68%. The exact rate where you achieve that's going to vary with your peaking time, and the recommended peaking time depends upon the detector. So that's where you see the detector-to-detector variations. All right, I believe I've answered all the questions that have been sent. Thank you for your time. Thank you for listening to the seminar. Thank you for your questions. I hope this was useful. Again, I would encourage you to refresh yourself, look at that older seminar, take a look at today's when it gets posted, and stay tuned because we'll be doing another seminar in 6 or 8 weeks that will be focused more on exactly how to set the parameters in Amptek's digital processors. Again, thank you for your time and have a nice day.